All right. Hello, good morning, or afternoon, or evening, whenever you're watching this. Today, we're going to cover assignment number 6. This is what was covered in class today, October 22nd, Thursday. My odd classes should have already finished most of this, and so this is just to update um, or give you guys a resource to go back to. Now, as part of class, I just want to remind you that assignment number 5 is due this Friday, the 23rd. This is the assignment on chemical changes as well as physical changes. We had watched a bunch of YouTube videos, determined the changes that were done in there, and you guys had the last 4 questions of that assignment to answer. So that's coming up due tomorrow, the 23rd. In addition, student-led conferences are happening tomorrow, and so every Schoology period, at least for chemistry, will have a student-led conference form for you to fill out with your parent as you attend the conferences from 12:40 to 2:15. This is entirely a student-led thing, so I will be available on the office hours like usual, but I don't necessarily need to be there. Now, as far as assignment 6 go, make sure you have that copied in to your notebook. Click on that link to get the copy, and we're just going to go ahead and fill this guy in. Go ahead and zoom in a bit. Here's assignment 5. We're answering 7 through 10 by Friday, so make sure that is filled out. And we're wrapping up here. So assignment number 6. This is honestly one of my favorite assignments, the assignment on mixtures. And the version you see here is a cut down version of what I would normally do. Unfortunately, with COVID, we can't really use all the resources we could. So kind of cut things down. Now this assignment focuses on mixtures, but before that started, you got to have an understanding of what is a pure substance in comparison to a mixture. And so we're going to use this image here to kind of guide us along. And so to determine the difference between these two, we want to ask ourselves, is this substance just that one substance? Does it have a fixed composition? And so if we take sugar, for example, sugar is carbon, hydrogen, and oxygen. It's got 3 elements in it, but they're all arranged in a particular order. And if all of our object is just carbon, hydrogen, and oxygen in that particular order, then we could say it's purely sugar, purely sucrose. Water, if it's just H2O, there's no other things inside of it, that's a pure substance. Salt, right? NaCl, sodium chloride. If it's just salt, there's no pepper inside of it, then it's a pure substance. And naturally, any element by itself, like if I had a block of gold, that is pure gold as a pure substance. And so here are some more examples, right? Powders like baking soda, crystals like salt. These are all examples of pure substances. And on the other side of that coin, we're going to have mixtures. Mixtures are basically a blend of 2 or more kinds of matter, and typically those matters have their own, keep their own properties and identities. So mixtures, we talk about them because there are a multitude of ways to separate out mixtures, but there are 2 varieties, homogeneous or heterogeneous. Homogeneous basically means these things are the same. Imagine a smoothie, right? You can't really tell one smoothie, one portion of a smoothie apart from another portion. They're all basically the same thing. Heterogeneous though, that's where things become different. And so homogeneous, homo, that's the root word there, means same. Hetero, meaning different. So if air is our example for a homogeneous mixture, that's because in air we have oxygen, we've got carbon dioxide, we've got nitrogen dioxide, we've got pollutants in the air, we've got viruses in the air. It's all there, but you can't really tell it apart. It's all the same, right? When you breathe it in, you breathe in everything kind of equally, and so that makes this a homogeneous mixture. Sugar and water, if you dissolve it, if you take a sip and then you wait a bit and you take another sip, it tastes the same, right? Stainless steel, it's all stainless, right? There's no one part that is going to have a stain on it. And so that makes this a homogeneous mixture. Oatmeal, right? Let's take oatmeal for example. Not oat meat, oatmeal. Um, let's take oatmeal. Let's take this version. If I took a spoonful of this, I would get a crunchy flavor, and I'd get some that liquid, right? And I take another bite, same thing. This could be argued as a homogeneous mixture. However, if I add some toppings here, this becomes heterogeneous, right? Because every single bite might be different. One bite, I'm gonna get some blueberries. Another bite, I'm gonna get some granola. Another bite, banana, right? So it becomes different every single time. And so here, I call this fancy oatmeal, same thing. A smoothie. Smoothie is a great example of a homogeneous mixture. It's got a bunch of things in it: spinach, kale, strawberry, banana, blueberry, sugar, ice, water, right? All of that's in there, but you blend it. And so it's smooth and it becomes uniformly distributed. Every single object inside there is uniformly distributed. And so that becomes a homogeneous mixture. However, something like a salad, right? Let's look at some salads. Every single bite might be different from the next. So let's look at the easy Greek chicken salad. One bite, you might get some cheese. Another bite, you get some chicken. Another bite, you get some tomato and cucumber. That's different every single time. That makes this a heterogeneous mixture. So let's talk about some other mixtures and how we could separate these things out. Obviously, I have these answers written up here because this assignment is done as far as I'm concerned. So this video will not take that long. It goes longer in class. So how would you separate iron nuggets from aluminum nuggets? The answers we got in class were varied, and so we've got some various answers. Magnets was the first answer, right? Magnets attract iron, they don't attract aluminum. Easy peasy, that's how you separate them. You could also use several other things to separate out metals from each other. Melting points. And so I showed in class a website called ptable.com. It's a really great resource. We've got all these kinds of data about these elements, and we can compare them. So let's take a look at melting point. The melting point for aluminum, you can see here, let's go ahead and click on that, is 660.32 degrees Celsius. For iron, it's 1000. And so that tells me if I want to separate these two out, I could just heat them up. My aluminum will melt, and then my iron will stay the same. Another way to do it, we've got density, right? Soak them in some water, right? Maybe blow some air on it. Iron's, over here. Iron's density is about, and I'm going to just reduce this to grams per milliliter. Iron's density is about 7.8, whereas aluminum is about 2.7. So if I took some air, like I had a can of air and I blasted it, my aluminum would fly off. My iron would stay the same. What else can we say? Conductivity, right? You throw some heat in there. Aluminum valued at 235 watts. Iron, about 80. So the conductivity difference is another way we could separate these guys out. Next up, how would you separate sand from styrofoam? You could wash it. Honestly, mixtures, they vary in terms of complexity, right? Separating iron from aluminum, it could be complex, or it can be as dead easy as using magnets. Sand from styrofoam, soak the mixture in some water, your styrofoam will float up. Alcohol and water, how would you separate this guy out? So alcohol and water, there are two different ways we could use this. Alcohol has a boiling point of 78 degrees, meaning at a certain temperature, alcohol will start boiling and you're going to get some alcohol gas flying around. Water boils at 100 degrees. So if you heat this up enough, the alcohol will boil off and you'll be left with water in your container. And the alcohol is gone into the atmosphere. The other way to separate out alcohol from water is to freeze your solution. If you freeze it, water freezes at 0 degrees, alcohol freezes at negative 114 degrees Celsius. And so if you freeze it, your water will be frozen, and on top of that water or below it, depends on density, um, on top of that water, separate from the block of ice, is going to be your alcohol. So that's two different ways to separate out this mixture. Now, for number three, we got to look at an image, and inside that image is a bunch of techniques. Go ahead and click it. A bunch of techniques that we use to separate out compounds. I wanted you guys to pick four and define them and kind of just provide an example of it. I've already done this here. We've got filters. What does a filter do? It separates solids from liquids. The example we have are if you have tap water and you got a filter over it, that filter takes up any lead, any fluorine, and gives you pure water. Coffee filters keep the coffee grounds out of your coffee. Easy. Magnets. Magnets are used to typically get solids away from other solids. They're typically used with metals or anything that is magnetic. So our example is when we're separating iron out from our aluminum. A centrifuge. Let me provide an image here. A centrifuge is basically a machine that spins something around very, very fast, like thousands of revolutions per minute. These machines are rather expensive, and so you have to be very careful when using them. Let me see if I can find a picture here. Yeah. And so they're used to separate out liquids in terms of density. So the most common example is blood, and that's what you see in this image. And they have to be balanced out. If you put in only one tube, as it's spinning, it's going to basically explode. And that's why you need to balance them out. If you put one vial in, you got to put one on the opposite side to make sure these are balanced. So they spin really, really fast, and the heavier things will end up towards the bottom, while the lighter things will end up towards the top. And so for our example here, if I want to examine blood, right, like the plasma inside the blood, I put it in a centrifuge. And so we'll see all of our red blood cells will go towards the bottom. Our white blood cells will stay up towards the middle. And our plasma, which is basically the water of our blood, will float to the top. This is very valuable when doing science, especially biochemistry, when we're trying to examine contents of the blood. To decant something is to remove a liquid from a solid. So for example, if I want to get rid of if I want to collect the plasma, I just tip my test tube over very gently, or I use a syringe to extract my plasma from the rest of this. And that's what it means to decant. You have experience of decanting things, right? If you've ever taken water away from pasta, that is decanting something. Distillation. Distillation is typically used on mixed liquids to separate out the liquid with the lower boiling point, right? So in the example with alcohol and water, alcohol has a lower boiling point, and so it's going to boil off first, and you could distill it, right? You could collect it in a test tube, not in a test tube, in a distillation tube. Oopsie, don't mean to do that. Typical distillation looks something like this. You'll have your mixed fluids right here. As you heat it up, one of them will boil up into a gas and rise up the tube. As it rises, it will start to cool down and then flow down this chamber. This chamber is called a condenser because it has cold liquids going through it. And so that will remelt or reliquefy your gas into a liquid, and that's how you get a distillate. Very similar to the next process called evaporation, again, which is also used on mixtures with liquids involved in it. And so an example for that would be an evaporation still, which separates out fresh water from dirty water. And so in class, I had the worst time spelling out the word separate. But let's look at a evaporation still for a second. The evaporation still is actually really easy to make. If you've ever heard of the game called, I think, The Raft, it's a survival game where you are on a raft and you have to make your own water stuck in the ocean. And the easiest way to do this is to basically create like a jug and then put some glass over it. Inside this trough, you'll have your seawater, and as the sun heats it up, as it's free from solar energy, it'll start evaporating. You'll evaporate off the fresh water and it'll collect on the glass. And as water builds up, it will flow down the glass into a collection tray. Here's another image. Let's get some color in here. Let's say you're on a desert island, you only have like cactus juice to, get yourself some water. You put your cactus juice in the hole, in a bucket inside of that hole, plastic sheet. As the sun heats up your cactus juice, the water will separate out and collect on the plastic sheet. And then it will drip down into your bucket. So it's a relatively straightforward concept and really useful in survival situations. The last one is chromatography. So for chromatography, let's go ahead and find the image here. Chromatography, nope, there it is. So for chromatography, there we go. Most useful for solutions, right? We base these solutions off of, how you say, as a gas, right? But it can be liquids as well and solids as well. These are mostly used for isolating colors and pigments, chroma meaning colors, and it was developed originally to separate out the pigments inside of a plant. And so these things are used to separate out mixtures of gases and vapors based on mass. And so we'll look at this image here. Let's see. Not this image. This is not very good. That's very small. There we go. So we take our plant here, we mash it up, right? We pour it into a vial of like acetone, which is nail polish remover, and our pigments here will separate out based on mass. So we have a lot of chlorophyll inside our plants, and so that will rise up slower than our smaller components, right? These carotenoids, these chlorophyll A's, alphas. So chromatography typically used to separate out mixtures based on mass. And that kind of idea is used all of the time in biochemistry in things like gel electrophoresis. We separate out DNA based on the mass of those DNA strands, right? If they've got like 1,000, like let's take a look here. We have some samples. We have a control where we know where all the masses are. Sample A, about 1,000 base pairs, pretty big. Sample C, sets of 3 DNA strands, with the smallest being 100 base pairs. And so it's a way to measure and separate out mixtures based on mass. This is the preview for the next step. And so the example for this would be to use gel electrophoresis to separate out smaller DNA strands from larger strands. Okay. And then for the last one, we watched a video, and this is the video that I really, really like because it's something that's so easy to do at home. It's half a cup of milk with a few drops of vinegar, and you could make your own plastic, a renewable source of plastic that is actually rather hardy. It's been used for a while. I'll let this guy talk for a bit.
This is a precipitation of casein from milk experiment. So I've heated the milk to 50 degrees, and I'm going to add dropwise 10% acetic acid. And when we hit the isoelectric point of milk, should be able to see a big glob of protein forming. So again, happens very quickly. I'm going to add one more drop and keep stirring. And this is done well. You usually get a very clear solution after the precipitation of the casein. And add another drop, see if I can clarify it anymore. It's probably pretty good. Again, you don't want to add the acid too fast because sometimes you can go right past the isoelectric point and not get, all of a sudden you've got a positively charged protein that stays in solution. But here you can see it's basically like.
Okay. And so that's the basic form of our plastic here. He mentioned something called the isoelectric point. I want you guys to just be aware that he's basically saying that if you add too much acid, the curd that you see here will go back into solution, and you're just going to have really, really sour milk. And so this is really cool because it could be formed into other plastics, and it's basically non-toxic and it's renewable, which is far better than any options that we have. Back in the olden days, like the 1900s, it was very common to see small knickknacks be made out of this plastic. They call it galolith, I think, stone milk, milkstone. And it's a very strong substance. Here's a plate, a shoehorn, a spoon, a comb, a pestle, I imagine, some dice, some game pieces, buttons. And that's obviously done with some processing involved. Regular casein plastics and molds. Regular casein plastics look a little bit more crunchy, but are still really, really cool to see, right? You could sand this off and make some really nice plastic pieces here. My favorite here is the skull. Casein plastics, all you need is a mold. A little stegosaurus, a little melted looking Lego man, but it's still really cool stuff, and it just needs a few refinements in order to get it to look pretty neat. And so what we're doing here, what the question is after adding vinegar, how would you separate out the casein? And in class, we decided on decanting the liquid to just keep the casein, right? That just means put it back in the beaker and just pour slowly to get the liquid out. Of course, you could also use a filter to separate out the liquid a lot better. You could dry it out naturally. And most of the time, you want to use a combination of these methods here. And now that brings us to the end here. Number 5 is a question I want you guys to answer on your own. What benefits does a renewable source of plastic like casein offer in comparison to oil-based plastic, which is non-renewable, right? What benefits does oil bring? And so in class, we mentioned ideas of just availability, right? We mentioned ideas of how expensive casein plastic would be, right? All the cows you have to make. And so that's it. Now, as far as the assessment is concerned, I'll be posting up the next video study guide tomorrow after our even classes have gone through it. That test will be released this Friday. Feel free to take it, but we'll have opportunity in class to take it as well because I'm aware that some people's home lives are not the best for taking a test. So we'd rather just spend some class time to do this. All right, and that'll take us to the end of Unit 1. Remember, our parent conferences are tomorrow. Make sure to fill out this form with your parents as you go through Schoology. And I'll see you all later. Bye-bye.